Hello everyone. Our speaker for today, we have the honor to have Dr. Simona Giacintucci, that has received her master's degree in astronomy from the University of Bologna back in 2001, and her PhD in astronomy from the University again of Bologna in 2007. From 2008 until 2010, she was a postdoctoral research associate in the High Energy Astrophysics Division of the Harvard Smithsonian Center for Astrophysics in Cambridge, Massachusetts. And then she moved on to the University of Maryland at College Park for having a NASA Einstein, a very prestigious Einstein Research Fellowship from 2010 to 2013. Currently, she's a research astronomer in the Remote Sensing Division of the U.S. Naval Research Laboratory in Washington, D.C., where she's part of the VLA low band ionosphere and transient experiment group. Her research focuses on low frequency radio and X-ray observations of galaxy clusters and groups, but I'll leave the stage to you. Let's welcome Simona.
Thank you so much for the introduction. Okay, let me share the screen. Okay, are you seeing it?
Yes.
Okay, I'll present.
Perfect.
Okay. Good. Yeah, so thanks again. And really, thank you so much for giving me the opportunity to talk about my work here today. I'll be talking about the extreme AGN outbursts in galaxy clusters. And as I know that there are students in the audience, I have organized my talk in a way that I'll give you first a very general, broad introduction on galaxy clusters and supermassive black hole outbursts in their central galaxies. And as I go through these introductory slides, you'll see that I have put some reference to very useful reviews on the topics, which you can have a look at if you want to have a more detailed picture of these topics. And after the introduction, I'll show you some recent results on the Ophiuchus galaxy cluster, which hosts the most energetic AGN outburst that we've ever seen in a cluster. And then in the last slides of the talk, I'll show you some very preliminary results on a joint radio X-ray study of another galaxy cluster that is called AB644. And here you can see the list of the colleagues that are involved in these works. Okay, so let's start with galaxy clusters. So clusters are very massive, extremely large structures. Actually, they are the largest structures in the universe that are bound by gravity. They contain from hundreds to thousands of galaxies in a region that is typically a few megaparsec across. But these galaxies, they only make up for a very tiny fraction of the total mass of a cluster that can be as high as 10 to the 15 solar masses, and which is dominated by dark matter. Some of this cluster mass is actually in the form of a very rarefied and superheated plasma that fills the space between the galaxies, and that emits X-ray radiation, which is shown here in the blue color. Now, as clusters are X-ray bright sources.
Excuse me, Simona. Yes? I'm sorry for. I think I'm only seeing the first slide. To be honest, is there maybe? Yeah, I'm sorry for interrupting you.
It's not. Oh, interesting. So.
Yeah.
Oh, okay. So you are still on the outline, or you are still on the title?
I can see the title, and I can see the slides on the left, for example. So this is the
so you are actually seeing my layout.
Yes.
Oh, interesting. Not because I'm using an external screen. What about now? Do you actually see?
Yes, perfect. Yes.
Okay.
Yes,
sorry about
it works.
that. I had no, because I was looking at the big screen. On the big screen, I have the presentation and not the layout. Okay. So anyway.
Thank you. Sorry.
No problem. Thank you. Let me know. So going back to cluster and X-ray emission, as I said, since the clusters are bright X-ray sources, we can, of course, use X-ray telescopes to study. And when we look at the X-ray images of galaxy cluster, in general, we can divide them into very broad categories, the unrelaxed and the relaxed clusters. based on the distribution of the hot X-ray emitting gas in the X-ray images. Here are two examples of each as seen by the Chandra X-ray satellite. In unrelaxed clusters, often the distribution of the gas is extremely irregular and complex. As you can see, we usually observe a wealth of substructures, clumps, multiple peaks, and sometimes shock fronts, like in this case, or shock-heated regions. And all these features are the result of a very energetic gravitational interactions between the clusters, in other words, cluster collisions and cluster mergers. Relaxed clusters, on the other hand, have not experienced very major gravitational perturbation, and so the distribution of the gas is much more regular and with a single bright peak in a center. However, even though they appear so relaxed on the large scale, they often have a substructure in their very inner and dense cores. Substructure that can be, for instance, created by the AGN, as we'll see in the next few slides, or by gas motions induced by minor gravitational perturbation. For example, the flyby of a small subcluster that does not perturb overall the gas distribution of the cluster, but perturbs the gravitational potential of the cluster and makes the gas in the center slosh in the center potential minimum, creating this very peculiar edge-shape fronts that we often see in the X-ray images of cluster cores and that we call fronts. Now, in this talk, I will mostly focus on this type of clusters, the relaxed clusters, which more or less account for about half of the clusters in the universe. Now, in this relaxed clusters, something very interesting happens in the very central regions. In fact, within, let's say, 100 kiloparsec or so from the center, we have that the temperature of the gas drops very rapidly. And at the same time, the density increases very sharply. And this behavior creates a very X-ray luminous region that has a radiative cooling time of a gigayear or less. And this makes this region thermally unstable. In practice, the gas in the center cools down, it contracts to maintain its pressure, it cools even faster, and then eventually it will end up flowing slowly toward the center along these cooling flows that deposit a large amount of cooled gas in the center, which eventually will turn into molecular material and stars at rates of thousands of solar masses per year. However, even though we do see the temperature of the gas cooling toward the center, this is an example of a gas temperature profile where you have the temperature as a function of the radius, and you see that the temperature of the gas decreases as we go toward the center. But this temperature in the center is not as cold as we would expect in this cooling flow scenario. And in fact, we have very little evidence for these large amounts of cool gas that are expected and the star formation observed. And this means that there must be some kind of a steady compensatory heating mechanism that prevents the formation of strong cooling flows and suppresses star formation. Several sources of heat have been proposed as plausible mechanisms to offset this runaway cooling. Some are listed here, but the one that is currently favored is heating by the AGN that is harbored in the galaxy that is at the center of these clusters. These galaxies are among the most massive galaxies in the universe. They contain supermassive black holes with masses up to billion of solar masses. And when the black hole accretes material from the surrounding, it launches a pair of very energetic jets that propagate upward that we can see in the radio band as synchrotron radio jets produced by relativistic electrons that are spiraling around the magnetic field lines. And that, as they propagate upward, inflate these very large radio bubbles or radio lobes filled with relativistic material and magnetic fields. In the center of clusters, as these radio jets and lobe move through the gas, they push away the gas and they basically create holes in it that are usually referred to as X-ray cavities filled by the radio emission. This is a very famous example. Is the central region of the Hydra A, where the radio source shown in magenta has created these large holes in the gas distribution, whose X-ray emission is seen here in blue, that are filled by the radio plasma. When the radio galaxy moves the gas, pushes the gas away, it makes mechanical work against it. And we can use the observation to estimate how much work it must have done to create, to displace the gas by measuring the pressure and estimating the volume of the cavity. And this PV work is basically a measure of the total energy ejected by an AGN outburst. And if we take this energy and we divide it by the age of the cavity that can be estimated from the observation under certain assumptions, we can obtain what is called the power, the cavity power, which is a proxy for the total energy that the AGN has injected in the gas. And we can then compare this cavity power to the luminosity within the very central region, the region of rapid cooling, and which is basically the luminosity that needs to be compensated for by the heating to prevent the runaway cooling. And we can see that on average, the mechanical power of the AGN seems to be enough to offset runaway cooling in most systems. However, how the energy of the AGN is transferred to the gas and how it spreads throughout the whole cool core, it's something that is still unknown. To complicate things, we now know that there are some AGN outbursts in some clusters that have been so powerful, so extreme, that appear to have deposited most of their energy at a relatively large distance from the center, beyond the region of rapid cooling. These are two, some famous example, striking example, for instance, MS0735 or Hydra A here, where you can see that the AGN outburst has been able to evacuate cavities that are as big as 200 kiloparsec across. So these are really, really large cavities. And the mechanical energy that is needed to displace such a large amount of gas is huge, is of the order of 10 to the 16 erg, which really makes these systems extreme AGN outburst. And the existence of these supercavities also strengthen, let's say, the need for a very fine balance between AGN outburst and cooling to avoid that, for instance, a very strong heating episode may overshoot the cooling rate and basically heat up the whole core, destroying the cool core. And so this suggests that this kind of heating and cooling feedback process must occur in some kind of a self-regulated way, in which the AGN heats the gas through some persistent and gentle injection of energy, and without destroying, therefore, the cool core. And the gas itself, the cooling gas, feeds the AGN in this self-regulated loop. Now, with this concludes my very broad and superficial introduction on AGN outburst in cluster, which I hope gives enough basis for the next part of the talk. And again, you can look at, there are several reviews listed here where you can have a more detailed picture of all this phenomena. And so with this, I will move to talk about our work on the Ophiuchus galaxy cluster that is, as I mentioned at the beginning, hosts the most energetic AGN outburst ever seen. A brief introduction on Ophiuchus. Ophiuchus is a very massive galaxy cluster. As you can see here, it's a nearby galaxy cluster. It's a relaxed cluster. It has a very dense inner cool core. You can see here, very bright in the X-ray. And the gas inside the cool core is sloshing, as is evidenced by the existence of this sharp spiral-shaped cold fronts. But the most intriguing feature of the Ophiuchus galaxy cluster is this concave X-ray edge here. You can see it. That was discovered by Norbert Werner and collaborators in 2016 using Chandra. This edge here could be the edge or the rim of a giant cavity with a diameter of about 500 kiloparsecs, simply estimated by the radius, the curvature radius of the edge, which Norbert and Werner and collaborator estimated that for which they estimated that a huge mechanical power of the order of 5, 10 to the 16 erg had to be required to create such a huge hole in the gas. And so they kind of thought it was too much and implausibly high to be really a cavity. But our later work done using XMM-Newton X-ray data and GMRT data and the GLEAM data as well showed that, first of all, the X-ray edge is seen also in the XMM-Newton image that you can see here in colors, and can actually be traced a little bit more than in Chandra. But most importantly, it showed that the radio emission seems to fill this region of the putative cavity at low frequency. Here you can see two of the old GMRT images that we produced at 240 megahertz at 2 different resolution, 45 a second into a minute. But what you can see is that basically this region, which is the assumed region of the cavity, appears to be filled by the radio emission. And so our interpretation was that this emission here is basically a giant radio lobe produced by an AGN outburst occurred in the center of the cluster that has produced also this giant cavity. You can also see that the Ophiuchus cluster is full of radio emission at all scales. There are extended radio galaxies with tail morphology, where the jets have probably been bent into a tail by their motion through the gas. There's a so-called radio mini halo in the center. These are diffuse radio sources that are not associated with galaxies, but they arise from relativistic electrons that are mixed with thermal electrons in the intra-cluster medium itself. And then there's a very interesting source that it's called the Radio Phoenix, which is believed to be a fossil radio galaxy that has been somehow re-energized and revived. But I will not talk about this radio emission. I will focus only in this talk on the giant radio lobe. As I mentioned, the energy that is required to create such a large cavity is extremely high, as shown in this comparison in this histogram that compared the cavity size and the associated PV work for a number of clusters with known X-ray cavities. And you can see that the Ophiuchus cluster that is shown in red is an extremely striking outlier in both distribution. The outburst has happened in the past and is currently off, as we don't see any radio jets coming from the center that feed the radio lobe. The central galaxy is currently active in the form of this very compact source of radio emission at the nucleus of the optical galaxy, which is very faint and has a size less than a kiloparsec, while the radio lobe here was instead created by a previous former cycle of activity of the AGN. And this is supported by the fact that it's a radio spectrum that is basically flux density as a function of the frequency, and this is my convention for the spectral index, has a very, very steep spectrum of 2.4, which is consistent with being a very old emission that is currently fading. And we estimated that the outburst that has created this fossil radiolobe has to be happening more than 240 mega years ago. So for us, this was like discovering a majestic dinosaur from just a little piece of a bone sticking out of the ground. Like for us, the bone basically was this little edge seen in Chandra that led to the discovery of something that is the analog of, I think, an Argentinosaurus for a paleontologist. And so on the wave of the excitement for this discovery, we went on and did some follow-up observations with the upgraded GMRT in a couple of bands. To first of all image the full extent of the radio emission and the fossil lobe in Ophiuchus to study its total spectrum and spectral index distribution, and to also search for a possible fainter counter lobe that was not currently seen in the previous images. And we also obtained new, deeper XMM-Newton observation of the area of the fossil lobe. And this observation was also requested for to search for possible cluster-wide effects of such a powerful AGN blast. So I'll start showing some of the results of the radio follow-up. So here you can see our deepest image of the extended emission in the Ophiuchus cluster is an image from band 3, centered on a frequency of 400 megahertz and with an 18-arc-second resolution. As I said, this is the deepest uGMRT image that we have of the Ophiuchus with a noise of about 25 microjansky per beam. And here you can see contours starting at the 3 sigma level. You can see how beyond all the radio galaxies, compact sources, and a large mini halo in the center, which is very well detected over the whole central region, we detect very well the bright and main part of the fossil lobe, which is just behind the X-ray edge that I'm showing here with an arc. Zooming on this region of the radic lobe, here are two slightly higher resolution images at 400 megahertz and in band 2 at 210 megahertz that show that the distribution of the radio emission within this inner region of the fossil lobe is extremely disuniform, non-uniform, and complex, and quite filamentary. In particular, you can see that there are these 3 prominent filaments, each about 100 or 20 to between 100 and 200 kiloparsec long, and with a width that is estimated to be less than 5 kiloparsec, as they are only 1 beam wide in our highest resolution image at 400 megahertz, which is not shown here, but it has a beam of 6 seconds. And so it constrains their width to be less than 5 kiloparsec. So they are very long and thin filaments. We obtain an image of the spectral index distribution between 210 megahertz and 400 megahertz, which is shown here in colors with the 210 megahertz contours overlaid. Again, this is the X-ray edge. And what you can see is that there is a very complex and messy distribution of spectral index. But what I think is interesting is that these filaments, especially the filaments F1 and F2, appear to be steeper with the spectral index, you see that in the color dark blue, than the underlying more diffuse and amorphous structure. And if we measure the total flux in this region at the 2 frequency, we actually obtain average spectral index for the filaments of 2.5, 2.8 for these 2, and 1.9 for filament F3. Again, this is the convention for the spectral index here. And if instead we measure the spectral index in the underlying extended region, excluding the filament, we see that it tends to be slightly flatter than the filament. Now, of course, when I say slightly flatter, this is really not a flat spectral index. A spectral index is 1.7 is actually ultra steep, and as indeed consistent with the fact that this is a very aged radio lobe that is currently fading and losing energy. We also looked in more detail at the filaments, looking for some possible trends, but we found that they tend to be quite uniform. Here you can see their spectral index profile extracted along the filaments going from inward toward the outer regions. And here you can see the flux density. And basically, they tend to be relatively smooth and uniform with a constant spectral index across almost the entire length, with maybe just some variation in between the first and the second part of filament F1. But overall, they tend to be quite uniform, unlike the rest of the extended emission that instead it's very, very complicated and irregular. So what's the origin of these filaments? We don't know. But as the synchrotron emission is proportional to the particle density and to the square of the magnetic field intensity, it's natural to think that they could either trace the underlying magnetic field structure, which must be coherent for a relatively large scale of a couple of 100 kiloparsec, or alternatively, they could trace a very non-uniform distribution of the particles in a very aged lobe that it's probably already starting to get more and more disrupted, possibly by motions of the gas, of the external gas, and during this very late phase of its evolution. This is only the brightest part of the lobe. As we know from our past GMRT images, the lobe extends further out. And so to try to map the whole extent of the relic lobe, we have produced low resolution images using our deep uGMRT data. Here I'm showing a composite image where in magenta, you can see the high resolution 9 arcsecond beam image with all the compact sources and the extended sources. And in blue, you can see an image that has been obtained after subtracting all the compact sources and lowering the resolution to about 120 arcseconds per beam. And the contours are also from the same subtracted image. You can see this is again as a reference is the cavity edge. This is the cluster center. You see that the fossil lobe extends, fills this region and extends further out towards southeast. But this is very hard to map. It's just a 3 sigma level contour. You see the emission becomes fainter and fainter as we move toward the outskirts of the cluster. This emission was actually already seen in a gleam, in the MWA gleam images, which you can see here in grayscale, and the red contours is the first 3 sigma contours of gleam, and the black contours instead are the GMRT image, low resolution, shown also here. And you see that the gleam emission also extends all the way down here, but at that time when we looked at gleam and we didn't have the sharper look of the uGMRT, we were not sure if this emission down here was actually part of the relic lobe, as the beam of a gleam is very large and we could not exclude the possibility of a blend of radio sources or something else. But now with the highest resolution and deepest uGMRT images, we can subtract all the contribution of the compact sources and we can map the lobe pretty well all the way to this distance, which is now basically 700 kiloparsec from the cluster center. And the radio lobes becomes much larger than we initially thought. It's now something like 500 kiloparsec in this direction and 650 kiloparsec in this other direction. So really, really huge. And we looked at the spectral index distribution over the face of the radio lobe, a low resolution, producing spectral index maps at different resolutions. Here are shown two examples between 210 and 400 megahertz at 30-second resolution and 60-second resolution. In both, the contours are the 210 megahertz contours, and the colors are the value of the spectral index. And again, we see that the distribution is extremely complicated, with regions of a very steep spectrum. This is the region of the filaments that we discussed before, but also region where the spectral index becomes a little bit flatter, like here around the filament F1, or possibly a flattening of the spectral index here around along the X-ray edge. But unfortunately, the 210 megahertz has not enough sensitivity to map the entire emission from the lobe. So we don't have information, spectral information in this region, except for a couple of bright patches at the very end of the lobe, which turn to be with a spectral index very high of 3 and 3.3. So we certainly need deeper observation to map better this missing area. But overall, what we can see is that there are not systematic trends in spectral index in these images, which is consistent, I think, with the fact that this is such an old lobe at a very late stage of its evolution, which is probably already breaking up, and where you might have different structures overlaid, whose contribution basically, excuse me, makes the distribution of spectral index extremely irregular. So waiting for deeper observations, frequency less than 400 megahertz, we can look in the meantime at the new XMM-Newton images in the X-ray band. This is a mosaic obtained on the region of the lobe. You can see here, I hope, the concave edge, that is the border of the cavity. We can trace it a little bit more, but we can't really see the whole cavity. Consider that we are in a region that is very far from the brightest emission. And here the contrast is so low that it's probably not possible to ever, at least with XMM-Newton, even with deeper exposure, see the whole cavity. Here is the radio emission at 400 megahertz at low resolution, with a source subtracted, overlaid on the XMM-Newton. Again, you can see how the lobe is just inside the X-ray edge and extends here toward southeast, reaching 700 kiloparsec from the center. What is interesting is that if you look at the X-ray image, in the correspondence of this extension of the radio emission, also the X-ray emission seems to be extended in the same direction. And it shows here an edge, which, I mean, I would like to be able to move the colors to show you that there is actually an edge there. But what I can do is to show you a profile, extract the surface brightness profile, extract this in a sector that contains this edge. And you can see that here at the radius corresponding to this, this location, there's a very subtle step discontinuity that corresponds to this feature here. What is this feature? One possibility is that this edge is the analog of what was found in Hydra A, so a weak shock produced by the AGN outburst. Here in Hydra A, a Mach 1.3 shock was found just ahead of the giant outer cavity and giant lobe. And so this could also be a weak shock produced by the powerful AGN outburst that has evacuated the cavity. Alternatively, it could be a cold front, like it was found in the cluster Abel 2142 by Rossetti and collaborators in 2013, who found this incredible cold front at about 1 megaparsec from the center. and created by very large sloshing motions on the entire cluster scale. There's a set of cold fronts also in an inner core. But the existence of this cold front out of megaparsec implies that the whole cluster is basically sloshing. And this could also be a similar situation in which this outer edge is a cold front created by a large scale sloshing. Now, to differentiate between a shock and a cold front, in principle, one could measure the temperature here across the edge and compare the temperature inside the edge with the temperature outside. And if you find a temperature that is hotter inside and colder outside, that would suggest a shock. If you find a colder temperature inside and a hotter temperature outside, that would point to a cold front. But unfortunately, this region of the cluster is dominated basically by the background, and the cluster photon statistics is totally insufficient to be able to measure any temperature with the current data. And so we remain, I guess, with the DAB for now, waiting for new observations in the X-ray, maybe with future X-ray telescopes. But in the meantime, we can start to try to find answer to some of the many questions that are still open about this incredible object. For instance, one thing that one could wonder is that if such a powerful AGN outburst that has been able to create a 500 megaparsec 500 kiloparsec big cavity, has also been able to induce effects on the gas over the whole cluster, some cluster-wide effects. In particular, if, for instance, if the outer edge is a cold front, is it possible that this cluster-wide sloshing was actually initiated by the powerful AGN outburst? And so we're planning to use some numerical simulation to model the AGN outburst and its possible effects on the ICN to see if the blast was actually able to produce this sloshing motion in such a large scales. One other question is what actually has caused this incredibly energetic outburst, and our colleague Norbert Werner, as he stated, the black hole has probably would have had to swallow about 207 million solar masses of material to create such a big blast, and that means basically a galaxy-sized chunk of matter. And it would be interesting to go and look for traces of such an accretion event of something that is like the size of a dwarf galaxy. Like, for instance, it was done in MID7 using planetary nebula distribution to infer the fact that the black hole had recently accreted a small galaxy. But unfortunately, I'm not sure how this can be done in the case of Ophiuchus, as it really sits in a very unlucky region of the sky. As you can see, it's just above the galactic center, which I believe is a nightmare for optical studies. But nevertheless, it would be interesting to check if it's something similar can be done also for Ophiuchus. And then I've told you at the beginning that we believe that the AGN and the heating and cooling process are somehow occurring in a self-regulated, gentle way, where to avoid that, basically to heat up completely the core and destroy it. So one could wonder how it's possible that with such a big blast, the cool core still exists, as we still see it in the X-ray images and the temperature profile. And one possibility is that the jets were so fast and so basically supersonic that they pierced through the cool core without interacting with it, so without disrupting and heating it up, and they have deposited all their energy outside the cool core, leaving the cool core behind basically intact. This, I think, is something that might also be possible to investigate with numerical simulations. And I talk about jets, plural, because typically AGN outbursts are bipolar with 2 jets and 2 lobes. So obviously a natural question if there is a counter lobe here. Our deepest GMRT images do not show any hint of a counter lobe, at least in the region that is opposite with respect to the center, which may suggest that the counter lobe, if existed, got disrupted and already faded away in a lower density gas on the opposite side of the core. But not the counter lobe doesn't have to be necessarily diametrically symmetric with respect to the main lobe. So for instance, we can look at other directions, and in this area here, you can see there is this region of very low brightness radio emission that, with a lot of imagination, one could possibly think it's the remainder of a disrupted counter lobe. However, we do not see any X-ray features in this region that could hint at a counter cavity in the X-ray. And finally, the biggest questions of all, if this cluster is unique, or if there are other dinosaurs out there that await discovery. And the ongoing and future surveys with the new generational radio telescope, as well as future X-ray observatories with large collecting area, have certainly the potential to discover more of these fossils of mighty AGN outbursts. And just to conclude this part, we've seen that somehow the cool core in Ophiuchus has managed to survive despite the most energetic outburst we have ever seen from an AGN. But there's a possibility that in some clusters, the AGN heating has actually been able to, may have been able to overshoot the cooling rate and ended up heating up completely the core, blowing up the core, in quotes. And it would be interesting to go and look for possible systems in which in which the AGN heating has managed to, let's say, win. And there are a few clusters which are good candidates to look for non-gentle episodes of AGN heating. And one of them is this cluster, AB644. So AB644 is a very interesting cluster. It's actually probably boring, but interesting at the same time. It's a cluster that is very, very relaxed in X-ray distribution of the gas. As you can see, it's very regular. It doesn't have many substructures. It doesn't have indication of a recent merger. It has a giant CD galaxy at its center, whose elongation is similar to the X-ray halo, which is something that is seen in the most relaxed clusters in the universe. There's a single CD galaxy, so there's basically no indication that the cluster has experienced a merger in the past, also in the optical. So it has all the characteristics of a cluster that should have a central cool core, like the one we've seen before. However, it doesn't have a cool core, nor in its X-ray image, which shows just a very flat central region here instead of a classical peaky emission that is seen in the cool core, nor in the temperature profile, where you see the temperature does decrease over the center, but then remains relatively hot in the very central region. The BCG, the CD galaxy, doesn't have any associated radio emission, which is also unusual for a cluster that is relaxed. And usually in cool core cluster, we see radio emission associated with galaxies. So this is also consistent with the lack of a cool core. And it doesn't have any X-ray cavities that could suggest the activity of an AGN. And so this led to the conclusion that in this specific cluster, the suppression of a cooling flow, it cannot be attributed to present-day feedback from an AGN. But could it have been a past energetic outburst of the AGN that has heated up the entire core of the cluster? And so to look for such past energetic outburst, we have looked at ABEL 644 with uGMRT in band 2. This is one of the resulting images at the central frequency of 187 megahertz. In yellow, you can see the optical galaxies. In blue is the radio emission at the resolution of 20 arc seconds, also shown in contours. This is the position of the central CD galaxy. This is a very annoying background source that's just projected onto the cluster and has a compact radio source associated with it. But we see that for the first time, we detect radio emission coming from ABEL 644, and a lot of it, as you can see, there's a compact source at the CD, what looks like a pair maybe of jets, the opposite with respect to the CD, and then this very long tail of very low surface brightness emission, a couple hundred kiloparsec long, that propagates toward the south. If we look at the spectral index of this feature, just using the in-band spectral index, or spectral index between 147 and 217 megahertz, so it's a very narrow frequency range. We have anyway a hint that all the radio emission that we are seeing is a steep spectrum. Both the CD galaxy has a spectrum of 1.3 and the tail has a spectrum of 1.7, which are suggestive of very old emission. And so we think that we may have found the fossil of a past AGN outburst in this cluster. We have just obtained new uGMRT observation in band 3 and 4 that will allow us to map at higher resolution this structure and also perform a detailed spectral index study. In the meantime, we can compare the radio emission to the X-ray emission as seen by our deep Chandra observation. Here I've removed the background source just to highlight only the emission associated with the cluster. So again, the CD galaxy with the two possible jets and this very long tail of steep spectrum radio emission that, as you can see, follows the X-ray elongation. We do not see in the deepest Chandra data any clear cavities in the central region. It was already known, there's though some substructure in the cluster. It was already known that the CD galaxy that is shown here in red is offset with respect to the X-ray peak, which is shown in blue, and to the centroid of the large-scale emission that is instead marked by a white cross. And this is an indication of motions of the gas in the core with respect to the galaxy and to the large-scale cluster emission. And so basically the cluster is, the core is sloshing. And this is also seen in this residual image that is obtained after subtracting a two-dimensional double beta model, which describes the distribution of the gas on a large scale from this image. And once the model is subtracted from the original image, you can look at the residuals. And here we can see this sharp cold front, which is associated with the sloshing of the core, and this typical spiral excess that is seen in sloshing cores. But more intriguing, we can see that there's some kind of a deficit in surface brightness in this region that if you look really hard, you can actually see already in the original image. Now, we don't know what this deficit is. It looks like it's partially filled by the radio emission. Here is shown in contour at a lower resolution to try to map its whole extent. And as I said, we don't know what this surface brightness deficit is. It could be an hydrodynamical feature created by the sloshing, or a tantalizing idea is that it could be a part of a giant cavity created by the past AGN outburst, and that this basically could be the heating episode that has been able to heat up the gas in the core of this cluster. And if really with a lot of cavities, this is really a cavity, a really order of magnitude estimate of the PV work that would be needed to create something of the order of 200 kiloparsec in diameter would lead to an energy of the order of 3 times 10 to the 60 erg, that is similar to the mechanical work required to create the outer cavities in Hydra A. So we will continue, of course, to investigate this cluster, but we probably will need deeper X-ray observations to confirm that this might actually be a real cavity. In the meantime, we'll combine our Chandra data and band 2 data with the new uGMRT band 3 and 4 observations to do a multi-band morphological and spectral study of this fossil radio source, estimate its the age of the radio outburst, and obtain a map of the temperature of the gas to look for possible shreds of the cool core that has been destroyed. But the bottom line is that this is a cluster in which the processes that are responsible for the disruption of a cooling flow, including AGN heating, may actually have completely succeeded and may have been able to not only counteract cooling, but overshoot cooling and basically destroy the cool core. And with this, I stop. Thank you for your attention and stay tuned, because I hope I'm gonna have more results coming, and thank you.
Lovely, great. Thank you so much, Simona, for this very detailed review for AGN feedback in extreme outbursts, and for this very nice talk. Thank you so much. Let me just say, if anyone has any questions, please, yes, thank you. Please raise your hands, or if you rather prefer, you can just write a question and I will gladly say it. So maybe just to start off with okay, something to ask just before, until people maybe they want some time to think of something. In the latest system, I can recall the last of after Ophiuchus, the latest system that you just showed.
Yeah.
Yes. Yes, over here. Is it so I would like to ask in general, specifically, but okay, make it in a more general question. How do we know here that the core is sloshing, or what has caused this core sloshing here? And in general, what causes a core sloshing? I mean, was this only due to the AGN outburst here, or maybe something else? So I'm just
there have been a lot of simulation of sloshing in relaxed clusters, and in general, they are set up by the, as I said at the beginning, by some very minor gravitational perturbation of the cluster. So imagine that you have a cluster that is, you know, relaxed and sitting by itself, and then some smaller subcluster passes nearby. But without, you know, something small that doesn't necessarily destroy the distribution of the cluster, but simply perturbs the gravitational potential. And this in general causes the cluster, the gas that is in the center, like in a glass of wine, imagine that you start to slosh back and forth, and it creates this cold fronts that we see in the X-ray images that are basically simply contact discontinuities between the gas inside the cool core and the gas outside, created by this motion. So these are subsonic motions that They are no shock fronts. They are basically just contact discontinuities. And in general, the sloshing in this cluster is attributed to some kind of perturbation by some perturber that passed nearby. In some cases, the perturber can be identified looking at the X-ray or the optical. In some other cases, it's not. Consider that some of the simulations, like the Ascasibar and Markevich simulations, the subcluster is even just can even just be a clump of a subcluster of dark matter without gas, and it will still induce this sloshing in the center. One question that we would like to understand is that, for instance, in Ophiuchus, and maybe here, if you have a very powerful AGN outburst that, you know, it comes and boom to such large scales, if actually this can even perturb the gravitational potential of the cluster in a way that the core starts sloshing. And this we hope to actually look at with the simulations. So in this specific case of ABES 644, as I say, this cavity, it's, I don't know, maybe it's my imagination that I want to find another one. Maybe it's just a substructure caused by this sloshing. But the major indication that the cluster is sloshing is that we see a cold front, and this cold front is also seen in profiles of surface brightness and temperature. So it's a confirmed edge. And I haven't shown them here, but we've done that. And also the fact that you have such a asymmetry, such an offset between the peak of the X-ray emission, where the densest gas is, and the centroid of the general distribution of the large scale, which indicates that the central gas is moving with respect to the larger scale gas distribution. So.
Great. Yes, thanks.
Question.
Thank you. Yes, yes, absolutely. Yes, thank you. Do we have any questions from the audience? No. Okay, I can ask one more. It's regarding the Ophiuchus cluster. This amazing system and this amazing finding. I noticed that there were a couple of structures, the Phoenix and the south west relic. Are they connected to this radio emission, or maybe they are not? And
okay.
And
yeah.
also, yes, exactly. Yes, these ones.
Yeah,
are
so,
they? Yeah,
it's a very complicated and you know, so yes, there's this emission in the center, the mini halo. There is this radio phoenix here with underlying some diffuse emission, which is really not clear if it's connected to this phoenix or it's connected to mini halo. You know, if we had not known about this X-ray edge here, this could have been possibly interpreted as a single structure with a mini halo in the center and maybe some ultra steep spectrum diffuse emission outside of the cool core. But the fact that this emission traces so well a high resolution, the X-ray edge, it suggests that this part is basically a physically distinct component. Regarding these features here is really hard. So this phoenix, if you look at the high resolution, it's like a very filamentary vortex-like thing. It's really, really strange. It doesn't have jets, cores, anything. Here at low resolution is just this big elongated banana, but it's really very disrupted. And it does resemble simulations of, for instance, a radio galaxy that has been crossed by a shock in which the plasma has been somehow revived by the adiabatic compression. And this, to me, is a mystery, actually, what this emission could be. I don't know, maybe it's part of the mini halo, or maybe it's the disrupted counter lobe. We don't have any spectral information about this emission because it's only detected in this very deep image at 400 megahertz. So I have no idea if it's if it has a spectral index like the fossil lobe or is similar to the mini halo. So we will certainly have to look with deeper observation, but yeah.
Yes, absolutely. Yeah.
It's a very complicated cluster.
No, indeed, no, absolutely. And if the jet, for example, has a different orientation, like you have just showed earlier, are there any indication for the gas, for example, in the north side to be more dense, or anything else in the X-rays that you might?
Yeah. So if I don't know if I have here, let me see my XMM. So it doesn't in this image. It's not shown. Actually, you can probably see it in this one. Sorry. No, here, sorry. I'll get there. There you go. So, well, it doesn't really show. Anyway, in this region of the cluster here, the density is lower than here. So the density of the gas, if you look at the Rosat image that I don't have here, or our newer mosaic that includes also the northern part, you can see that here there's a brighter emission than on the opposite side. So this is a very region of low density. And so if you have a region of lower density, it's probably, you know, if you are in a region of higher density, the gas can somehow contain the radio emission. And so it can slow down the aging. And so you tend to maybe be able to see for longer time the emission. This, for instance, was suggested for the dying radio galaxy that are in the center of clusters where, and you know well because you worked on some of them, where you know that one possibility is that the fact that they are in the center of a cluster in a dense environment, the radio emission is somehow confined and it survives longer than if you put the same radio source in a lower density environment, for instance, outside of a cluster. So the differences here in in density of the gas may play a role in how long we are going to be able to look to detect this radio emission. And even along the cross, the extension of the whole lobe, we have a huge change of density going from this region to this region. And so this region, I suspect it's more confined, and that's why we see it still so bright, with respect to the outer region of the radio lobe, where it's probably already just fading and getting disrupted. Yeah.
Yes. Yes, absolutely. Yes, thank you so much.
Thank you.
If there is nothing else from the rest of the people, okay, then let's thank our speaker for today. Thank you very much, Simona, for this lovely talk.
Thank you for giving me the chance. That was nice.
Thank you. Thank you. Thank you very much.
There's a question from Keegan. Okay, that's fine.
Okay, is there? No, I don't see anything. Sorry, Sam, do you see a question?
Yeah, Keegan has a question.
Okay, yes.
Yes, hello.
Hello.
Can you hear me?
Yes.
Yes. Well, first I just want to say hello, Simona. I'm the Keegan that has been in contact with you about mini halos.
The Keegan, yes. Hi, nice to meet you.
It's nice to meet you. I just wanted to say hello, and also just wanted to ask if a cool core does get blown up, like in a 644, what happens to the mini halo? Would there have been a mini halo to start with, and would it have been blown up with the cool core?
So about 644, there's no evidence that it has currently any diffuse emission in the form of a mini halo. What we are seeing, it looks like more of a also. Let me go there. 1 second. Okay, looks more like emission associated with the galaxy. But yeah, you're asking, so if you had a cool core and you had a mini halo like other cool cores, what would happen? That's an interesting question. I don't know. I don't know. I'm guessing. So if could it be that the mini halo turns in something like on, because mini halos, they tend to be somehow confined. to the cool cores, right? So although we have some evidence that in some cases they can be larger than we initially thought, but in general we see them like confined by the sloshing confronts in the cool core. So if you destroy the cool core and you destroy basically this confinement, it may be that the radio emission has, you know, if you have enough turbulence and you have enough reacceleration of the particles, they might maybe survive and actually get a boost and maybe even become bigger. But yeah, I actually don't know. I never thought about that.
Yeah, it's interesting. Maybe that's a way that a mini halo could transition into a giant halo.
Well, yeah, I mean, we have cases like of clusters that have this multi-component, right?
Yeah.
With a kind of mini halo-like emission surrounded by a much larger halo. Yeah, maybe you know, we see also some kind of very messy emerging cluster that seem to have like about 2319, I believe, that has something that it's more compact in the center, like a mini halo, and then the larger halo. So maybe you're right. Maybe this could be a way to still have like a multi-component source with a mini halo-like emission related more to the properties of the central core, and instead the larger halo to the overall cluster. But maybe, yes, maybe some kind of transition could also be associated with this events of heating up of the cool core, or whatever the process is, if it's AGN heating or sloshing or something else. Yeah, interesting comment. Thanks.
Okay, thank you very much.
Thank you.
Okay. Thank you very much. So if nothing else is there. Okay. Let's thank our speaker again. Many thanks.
Thank you again.